coasters, stunt drivers, and many other instances use the knowledge of a looping or a roller coaster to secure safety at those instances. For example, take the roller coaster. The makers of this roller coaster have to be 100% sure that it's safe, or else, well, people could and will be endangered, as they will fall out or something. We were wondering from what height a certain object completes a looping, and what energy this object needs.
Our PWS is therefore about finding what the energy is the object needs when rolling from a looping, rolling from a ramp into a looping, and then completing it. It is also about what the formulas is, what they are, and about how they are applied. Of course, we also need to know how it really works in reality and not only in theory. So that we also researched about that. The idea, well, we are both quite a fan of riding roller coasters, big ones, small ones, all kinds of roller coasters. We also both play Roller Coaster Tycoon. It's a game about making roller coasters, and the big thing is designing them. So that's really where our idea came from. So we started brainstorming a little, thinking about what are roller coasters famous for, and we came to the idea of the looping.
Like, this was our main setup of the experiment.
This was our first idea, basically. We modeled this and lived out.
Well, without the explosion, of course.
Yeah, but, without the explosion. That was planned at least.
So we were wondering what forces work on the marble when it's rolling down the track, and when it's on the top of the looping, like, why doesn't it fall to the floor instantly? And so our journey began with this idea in mind.
Yes. Oh. And of course we have to do tests. So we would like a volunteer from the public. Someone would like to volunteer. Timer. If you could just hold it straight up. Excellent. I'll go and stand over here so people can see it. Would be a good idea, I guess. Well,
this was our main experiment.
this is our first thing.
Well,
And it didn't work, just like our
this was
experiment.
probably too low
Yes.
for the car to get enough energy to make the looping.
And maybe we had a bigger looping,
So now the looping is smaller.
aiming at one person. Well, almost, yeah. It almost worked.
That's good enough for
Yeah.
our.
Yeah, because it didn't go right at the first time when we tried it as well.
So this was our main setup, our first setup, our start basically. And well, it's, as you can see, fairly inaccurate as well. The whole track was a little bit loose, a lot loose, and well, the angle wasn't fixed that the track made with the looping. And well, the theory is difficult to apply when this is so inaccurate. So we had to come up with something else to make our test more accurate.
Yeah, the looping wasn't fixed, so we had to secure it to the back of a wooden plate. It was mounted to the wall next to the biolab. Yeah.
Well, our main aim was to find out to what extent the theory matches, well, the results in reality. Like, the theory says that the marble or car will make it from a certain height, but maybe in reality that doesn't work out at all because of friction forces. So our main goal was to find out at what energy, like what height directly corresponds to energy. So what energy a certain object needs to complete the looping.
So we have, so then we constructed our main question, our main aim. That it goes as follows. To what extent does the theory match the experimental result regarding the amount of energy needed at the start of the looping for an object to complete the looping? This basically means, how high do we need to let the marble go or object for it to make the looping? We also had a sub-aim, from what height does an object need to be released, and thus what energy does an object need to have to complete the looping? Yeah, that was what I just explained, but in a simpler form. This our first setup, like almost first. The very first one was just we put a track together and just did some things.
We just attached it
Yeah.
to those metal bars.
Yeah, scaffolding we called it.
Like almost what we could hear, but then a little bit more.
It was meant to find out the best way to do the experiments. We tried some things. We tried using a computer program to track the ball or marble or a car, but that didn't really work to do to these things being in the way, the giant metal bars. So we have a few videos here.
Turn up the light.
This is the original. Yeah, it didn't go very well. I will skip ahead for a second.
So this was
Crash.
Yes, and then of course this is not what we expected to see. Yeah, this is really how we saw what it really was.
This is how it felt for us.
Yeah. Yeah.
Nee, dat dank ik.
This setup also made us realize that we had to attach the looping to a wooden wall, or else, well, it's not really accurate again. So our main setup looked like this. We had put white paper behind the looping so that the tracking would be possible. Because we use a program, Coach 7 or Coach 6, we used both of them. And there you had to have a strong contrast between the marble, which we dropped, and the background. So we used the white background. Also, we decided to not use the car has, well, 4 wheels, and the wheels generate rotational energy, or they lose part of the energy due to rotational energy. But the car has 4 wheels, or our car has even 8 wheels, and this made it a lot more difficult for us to calculate the correct energy needed.
It made it practically impossible for students like us. But we did use a 210 frames per second camera for more accurate results. And the rotational energy that Hidde said before, it is the energy, basically what is lost through rolling, like a marble rolling, and wheels, like I said before.
A sphere or a circle.
Yes. As we said before, we ended up not using a car at all, because of the rotational energy being way too difficult. So we just used the marble. As you can see here, this is the car part. We did film it, but eventually we didn't use it. Very exciting. And just like the marble, you can also see here why we need a white background. Yeah, we can barely see it even with the white background, but the program Pws 7 can distinguish the two.
So now Coach 7. Well, we used first Coach 7, but this version wasn't really accurate, as we couldn't smooth the graph. Like, the program basically makes this picture out of, well, the marble, which rolls like that. But, well, this isn't really accurate, and with Code 7 we couldn't smooth this graph. So we had to de-install Code 7 and install Code 6, because with Code 6 it was possible. And then we could smooth the graphs, and then we could get the numbers out of the graphs and make other calculations with those numbers. But now processing the results, well, all these numbers were results out of the graphs, but then not like 20 of them or something, but like 200 of them.
So way down.
And then we had to make all kinds of formulas, and well, all kinds of things happened. And we had to do this for 27 different, well, graphs.
Graphs, yeah, 27 different tracks. Yeah, we filmed it 27 different times, and yeah, that's a lot. And I will quickly explain what these numbers mean globally. You have here in the first thing the velocity of the y-axis, so how fast it goes up, from up or all the way to down. You've got the velocity in the x-axis that goes from left to right, right to left. Then you've got the overall velocity, the total velocity it has. Then we have gravitational forces, kinetic forces, so how much energy it has to move. We've got we've got Q, as in joules, it's the heat energy in our case. It contains more different energies, but we just assume it was heat energy. We've got here some numbers necessary for the rotational energy, which we explained before. And out of all that, we made two graphs with a couple of lines in it.
Well, our conclusion is that our final results were a little bit odd, because friction force decreased at a certain point, the warmth decreased at a certain point, which means that the warmth would be transferred into the marble again, which is odd because, well, it can't really happen. But our main conclusion was that there was a 50% increase in required energy, comparing the theoretical results to the reality results.
Now, we also, now that we know that, when we did know this, we had a question about, is this also the case for smaller loopings or bigger loopings? Well, we did a quick test because we were running out of time, and we came to the conclusion that yes, it was the case. Also, roughly 50% increase in required energy.
Well, this is the end of our presentation, and we hope you enjoyed it. Any questions?
Yes, thank you for your presentation. You did a lot of calculations, but I'm a bit lost on exactly what you calculated. So, your research question was, how does theory relate to experimental results, right?
Yes.
So why would you research that? Is that because you think theory is bad, or do you think it's just we want to measure the effect of everything that's non-ideal?
Yeah, we were wondering what part friction plays in this whole thing. Like, you can calculate with theory, like gravity is this huge of a deal, and well, this and this is that. But we were just wondering, how big is the friction in this experiment?
And there were no theories already that you could have used. There's a need for. I'm just teasing, but what is that?
What do you mean?
Well, I mean, there will probably be theories on the amount of friction and what it is. And
Yeah, of course there are.
Yeah.
Well, most of the world is already known nowadays.
But you wanted to calculate it for yourself.
Yeah.
Okay.